Hi everyone, this is Hawk. Today I'm gonna introduce an enhanced adversarial strategical timing attack against deep reinforcement learning. So this is a joint work from Georgia Tech, from me and Junqi, Dr. Pingyu Chen from IBM Research, Dr. E.O. Yang from Preferred Network America, Chao-Han from Columbia University, Professor Qinghua Li, and Professor Xiaoli Ma from Georgia Institute of Technology. So I'm gonna introduce the motivation and reinforced learning based adversarial example and the new attack methods. So first of all, so what is adversarial example against deep reinforced learning? So adversarial example is some mysterious small noise which is subject to degrade or manipulate temporal reinforced learning system. So the output of reinforced learning system is the action. So it's like up, right, up plus right. But under some adversarial attack, so the manipulated output action could be left. So like suppose we use a navigation system, but under a certain attack, so the action will be incorrect, so it will be really harmful. So how the reinforced learning made this direction is, for this example, the Mario made the example based on the scenario sequential frames. So how to calculate and giving some attack on this system could be highlighted as a virtual security and some resilience constant. Yes, as putting action and giving incorrect prediction like this one. So today I'm going to introduce the current methods of adversarial attack, and I will introduce two kind of new adversarial attack. One is based on online learning, one is based on the adverse evolutionary attack. So both one is the first one is a white box attack, which means we have to access the parameter of the model. The second one is a black box model, so which will be the really first generation of black box attack on reinforced learning. So we have some performance and discussion. So for example, how to find a model weakness of reinforced learning. So say we have an agent like this baby. So the baby is gradually trying to learn to work. The problem is when the baby almost learning to work. So it's kind of shaking, but at the moment it's almost learned to work. But if we can estimate this moment and we kind of push this baby or touch this baby, the baby will be really hard to work and never learn. Possibly at this period, it's hard to or never successfully to finish this working task. So previously, there's a method by Lin and his collaborator. So they used the potential function in the machine learning. So they calculate the Q function as a online learning based function, and they have this the maximum potential and the minimum potential energy to estimate if the best action of this baby is learning to work, with giving a lot of reward. But the minimum expectation of this action is really low value. So if this difference is bigger, the difficulty of this, the unbalanced unstability of this baby at that moment is this robust. So they're trying to estimate the time and the state, and they're adding this intervention or perturbation on this state. But this one I use the previous reinforced learning based gradient methods to generate this perturbation. But since the previous methods they form the reinforcement learning attack as a continuous and online learning process. But we find out the interesting thing is they can actually formula as a weight majority algorithm. So we consider the weight and majority each time we try to adding or updating the estimated the potential energy estimated function. So that could be like this. So when we have like several experts, so for online learning and weight majority algorithm, each time we're trying to give this voting. So the weight of the voting will be whether will attack or will not attack. And we gradually update this weight and the function even we put this reinforcement online, attack online, so they can be gradually learn to attack. So we propose a weight majority online learning attack on the original weight function, original and potential energy estimate functions. So each time we only also have the weight of the algorithm. So it's still trying to have this molded on both sides and then have the most smoothly estimated. And then we can have a position here. So assume the total number of the round, they have a inequality here. So the weight algorithm will have a bound like here. So the regrade will equal to the sum of this one and the minimum weight of this one. So they have a maximum bound. It will small or equal to square 2 times log d times n d. So this is the first time we have a proof on the bound of the weighted the potential estimate based attack. And then based on this, we have our algorithm, which is the adversarial online learning attack based on the weighted majority algorithm. This is the first algorithm, is a white box attack. The input is the number of aspect, which is a d. Number of the round is the iteration, is a t. And the threshold constant is the b. So we gradually estimate the threshold, and trying to initiate the weight and gradually update. Yeah. The one thing in the previous paper didn't this constant is by trial and error. But in our methods, we try the constant from 1% to 50% and find out around 30% to 40% have the best threshold constant. And the second attack is a parameter exploring policy gradient, which is directly attack the observation. So the reward is the upper side of the original reward. And so imagine there's another agent trying to minimize the loss function. So the other adversarial one, so they have made the other selection of this expectation function. And then we generate this h from the policy gradient. So for the agent, they're trying to maximize this expectation is equal to minimize the original reward and original expectation of the agent. In this sense, you don't have to access the parameter. Only pick out the observation here. So and then you can pick out the gradient and do the policy gradient. So let me introduce our environment. The first environment is based on a 3D rendering environment from the Unity. So the task is you have to access the yellow banana, and at the meantime you have to avoid the blue banana. So if you access the yellow one, you get +1, and got the blue one, you got a reduction of the -1. You can see this small box here. So they actually have some observation of the razor tracing, and the distance of the object and the distance of the wall and your velocity. So the total observation state is equal to 37. Also, the other robot learning environment is the multi-robot arm control. The robot arm have to control this ball, and for all these arm, so around 10 arms they have to control this ball against the position and the gravity successfully. So we have to follow this waypoint. So in this environment, we have 33 dimensions, and action space continuous action. So here we can do this policy-based learning like A to C. So the third one we use it for this robot learning is we trying to learn navigation in an embedding system. So here we can actually find out the body can actually simulate it and train it in offline, and you just put this algorithm in your Arduino-based car online. So this one we're trying to simulate an autonomous system. So first we offer the clean observation, and then we get noise observation, the zero-odd random fusion, and adversarial perturbation like the previous study. And we can find out in the performance of decay the performance. So the weighted majority algorithm have really effectiveness. And our black box attack have the competitive result in the previous paper by Lin in EJK. But our result don't have to access the parameter. So the environment we use is Unity 3D banana collector. And both results are on the DQ and A3C. They can compete the result. So WNA, the weight majority algorithm, had the best result. Following by EJK paper, our first black box attack. The conclusion is majority algorithm is competitive to enhance timing attack, and black box attack is possible in the timing attack setting. So we have to do more theoretical study. Future work can be evaluate the cost of attackers. Thank you. Let me know if you have any questions.